All right, so instead of doing a super duper formal proof, here's how I like to think about this particular result. So here's a picture that I'm hoping is helpful. It's kind of a weird graph of the x-axis is the arms. In this case, this is a 5-arm bandit. And the y-axis is the value of that arm. And these rectangles represent our uncertainty intervals of that arm's value. Does that make
Okay.
sense?
They're not the arms themselves. That's just the uncertainty.
Yeah, if they were actually arms, then I'd have to draw like. Oh, that's terrible. That was supposed to be a hand, so I apologize.
That's a 7-fingered hand. That's okay.
Yeah, I think that was the problem. Because you know what it is to make up for the fact that like Mickey Mouse only has 4.
That's perfectly reasonable.
So if we do this, if we make sure that each arm we are 1 minus delta over k sure that its estimate is within epsilon over 2 of what our sampled evaluation is. So how big are these bars exactly?
Oh, okay, I see. So those are uncertainty bars or error bars. So that means your estimate is right smack in the middle of each of them.
Right. So we have our estimates for each of the individual arms, and that estimate is, we're pretty sure, epsilon over 2 close to the actual value.
Right. So that would mean that you could be epsilon over 2 too high or epsilon over 2 too low, which means the total height of those bars is 2 times epsilon over 2, or epsilon.
And those estimates hold true with some probability.
Sure.
So each one is correct with probability 1 minus delta over k. So the first thing we need to do is basically make sure that all these estimates are correct. Because if one of them is wrong, then it casts doubt over the entire calculation. So what's the probability that all of these estimates are actually correct simultaneously?
Well, if I pretend they're all independent of one another, then isn't it just 1 minus delta over k to the k?
Delta over k is the probability that a given arm is wrong. 1 minus delta over k is the probability that that arm is right. So if that probability is 1, for example, then raise that to the k power. Sure, they're all going to be right because they all have certainty of being right. But if it's a little bit less, 0.95 or something like that, then it's 0.95, and this one has to be right. That's another probability 0.95, and this one has to be right. So we end up with the raise to the k power of that individual arm probability.
Right.
It turns out for various reasons that this kind of quantity is hard to work with, and also sometimes, I think not in this case, but sometimes it's also a little risky because it assumes statistical independence of all the estimates, and sometimes it's safer to just say, maybe they're not independent of each other. Maybe they actually all fail together or all fail separately. So we use a standard trick to get around this idea. And this is the idea that we can estimate the probability that at least one is wrong. If we know the probability that one is wrong, it can't be, since there's k of them, it can't be any worse than k times delta over k. And this kind of follows from, if you think of it as like a Venn diagram, there's, here's the probability that one thing is bad. Here's the probability that the other thing is bad. Here's the probability that the third thing is bad. What's the largest that this can be? The maximum badness probability is actually going to be the sum of these if their intersections are all 0. And so this is really like taking the union of all those sets. So this is referred to as the union bound, which, I don't know, to me sounds like kind of a fancy name for not such a fancy idea. We're just going to add the probabilities because we don't know how to account for the overlaps.
Oh, but that just follows from probability, right? The probability of A or B is just the probability of A plus the probability of B minus the probability of A and B. And sort of the worst case in this situation is that A and B is 0.
Right. So this is just how these probabilistic quantities are defined. And what we're saying is if we want to maximize the probability of this or, that at least one of them is wrong, then if we set this intersection as 0, that maximizes it. So it really is just the sum is an upper bound.